And this is a very important part of in mathematics associated with this law of cosine. So I really need to just mention this a little bit about this important. It's more important than law of sines. Here's law of cosines, and let me start from the Pythagorean theorem. Everybody knows Pythagorean theorem, right? Pythagorean theorem is for what kind of triangle? Right triangle. So law of cosine is a slight generalization of that result taught to every triangle. Pythagorean theorem is only for right triangle. Law of cosine looks like Pythagorean theorem, but it is for every triangle. It's an important result in geometry, and that is used in Calculus 3. There's a 3-semester of calculus courses. In Calculus 3, the huge geometry is a part of this study, and something called the dot product you will see that is equivalent to this law of cosine. Important part of the geometry, an important part of the classical mechanics in physics. So that's easy to understand. And later, mathematicians think a lot about the geometry. This is so-called non-Euclidean geometry. And physicists and the people who were dealing with the real-life problem didn't care about this type of thing in around 1800. But it was mathematicians daydreaming and like in Alice in Wonderland, to create this weird world in their heads using this idea of a dot product, and which is succeeded by Riemann. You will hear his name a lot in calculus courses. So this was just out there created by mathematicians. Then later, Albert Einstein, his vision and idea, and he realized that their setup is a perfect for the geometry of the space-time. So he used this 1800 accomplishment of mathematicians, and early 1900 Einstein realized this idea, general relativity, using this everything that's built up in there. So behind all this thing there is this Pythagorean identity, Pythagorean theorem, and law of cosine. That's what we're about to learn. Let me start with this triangle example. What you're looking at is a right triangle. Theta here indicating this angle 90 degree. And the main theme of this algebra and trigonometry is that geometry problem is embedded into xy plane. We did that a couple times. So we embed this right triangle such that the right angle goes to this side like this, and this side is overlapping axis. This length here is supposed to be a, therefore this point here is a comma 0. Does that make sense? Right, a comma 0. That length is b, therefore this point here is 0 comma b, right? 0 comma x equals 0. And this is the hypotenuse of the right triangle, correct? What we're going to do is that we're going to keep this length and a the same and just change this angle slightly smaller. So notice that I draw a circle with radius b, and I draw a smaller circle with radius a so that it goes through that. This never changes. This side will be leaned slightly towards the right like this, and I hope you see that this b here, that b is the same because it's on the circle. Radius is the same. A did not change. That angle changed to something else, theta 1, less than 90 degree. And this side is no longer called opposite side. This side is called no longer called hypotenuse. This is now just called opposite of theta 1, right? Theta 1 is here, and C1 is opposite of that angle. Make sense? And B did not change, A did not change. Theta changes, the smaller one. Therefore, I claim the C1 changed, the opposite sign changed. Here's a comparison, and I will explain what this picture is. Alright, the blue circle has centered right here. What is the coordinate of this one? A comma 0. Right? So I'm going to go where the blue circle is. So blue circle is up there in the North Pole. So that was a C before, right? The hypotenuse of the right triangle before in here. You see that? That's a C. Now, if you keep B and A and make this angle slightly smaller than 90 degree, called theta 1. Opposite side is different, is C1. And then this red circle is centered at the same position a comma 0, and at this point draw the circle, so that you can compare this length and that length. The blue one is the hypotenuse, and the red one is now new opposite, and you can see that got smaller, right? So what happened if you keep these two adjacent side and make the angle slightly less than 90 degree? What happens to the opposite side is getting smaller, right? So if you squeeze the angle even further down, you can see the red one is still centered at this origin with this radius, far smaller than the hypotenuse one, right? It's getting smaller and smaller. So what is the relationship between A and B and C1? Is there something like a squared plus b squared equals, c squared and blah blah? Is there something like that? And that's the law of cosine. So let me go to the other side. Over here is greater than 90 degree, right? And this blue circle is again going through the hypotenuse, the original hypotenuse. Now red circle, as you can see, is hitting this new opposite side. Got bigger or smaller compared to the hypotenuse here? Got bigger to the center. So if the angle is greater than 90 degree, what happens to the opposite side is opposite side getting bigger and bigger as you go push further over there to there like this. Does that make sense? That's the qualitative discussion of what is happening to the opposite side if you vary your angle of the of that adjacent side. All right? So what is it? What is that adjustment? But first we're going to make sure we understand this relationship clearly. So I'm going to write it here and make it as a first exercise today. A squared plus b squared equals c squared, Pythagorean theorem, and those are the sides of the right triangle. C hypotenuse, A and B are the two legs, two adjacent sides of a 90 degree. Now if you squeeze that angle slightly smaller than 90 degree, and this A and B never changes. So a squared plus b squared in this squeezing scenario, that never changes. But C1 is a new side, there's opposite side. They're not the same, right? They're only the same when it's a right triangle. Which one's bigger? If the angle in between A and B, if that's greater than 90 degree, a squared b squared never changes, but the opposite side, C2, is different from C. Which one is bigger? So you have to make that decision. They're not equal. One thing is bigger than the other. Making this choice is your exercise. All right, what's your verdict? If theta 1 is less than 90 degree, and these two T-points are getting closer and closer to each other, right? As you get smaller and smaller. So what happened to the C1? This never changes as so this is smaller. C1 squared is smaller or greater? It's supposed to be smaller, right? The other one is greater, and that's the correct answer. Yeah. Very good. So that's a qualitative discussion of law of cosine. So here's something. Here's I have a triangle. Now this C is not that C. It's just the C is opposite side of the theta there. Okay? And I have these two adjacent side AB. Now if you write C squared over here and compare that with A squared plus B squared, and you know in general this is not true, right? Only when theta is 90 degree. So if theta is smaller, then do we have to add to the right hand side? If theta is smaller than 90 degree, do we have to add to the right hand side so that it's equal? Less than 90 degrees here. This is bigger, right? Than c squared, opposite side. So what should we do to the right hand side so that they're equal? You have to subtract off something, right? So that they're equal. Does that make sense? It's adjustment amount. A squared b squared plus b squared is greater than the opposite side squared. So you have to subtract off a little bit so that they get equal to each other. If theta is greater than 90 degree, you know the left-hand side, c squared, is bigger. So you have to put something on it here, right? Such that they get equal to each other. There's this adjustment to this Pythagorean theorem so that they are actually equal to each other. And that's the shape of a law of cosine. Right? So here's the law of cosine. And this is what you need to keep in mind and remember, memorize. Law of cosine in there. Alright, here it is. C squared equals a squared plus b squared. That looks like a Pythagorean theorem. But what is the adjustment amount? Negative 2ab times cosine theta. This is the adjustment amount. If you throw this term in there, they're perfectly balanced, left-hand side and right-hand side. And this formula works as it is exactly for all the angle between 0 and 180 degree. Alright, let me explain what happened in different coordinates. Maybe I can get that one there. Alright, if your angle theta is in here in the first quadrant, what is the sign of cosine theta? Is that positive or negative? This is a positive number, right? Cosine is x coordinate. So if your angle is over here between 0 and 90 degree, the cosine theta is going to be positive, right? So if you go in positive here, that cosine theta is positive, so you end up subtracting it. And that's what we discussed over there. If your theta is over here, like this, what is the sign of cosine theta? Negative number, right? So if you put negative number there, it end up being adding to the right-hand side. So that's what we have discussed there. Okay? What is the cosine of 90 degree? Anybody remember the cosine of 90 degree? This is x coordinate on the unit circle, right? Where's 90 degree? 0 is over there. Is exactly, this is where x equals 0. So that is 0. Sorry about this. Terrible notation. That cosine of 90 degree is supposed to be 0. That's what I'm saying, right? So if you put 0 in there, what happened? Becomes Pythagorean theorem. Yeah, when theta is 90 degree here, cosine 90 is 0, becomes a Pythagorean theorem. Disappears. C squared equals a squared plus b squared. So you don't have to do anything about this AB thing. Just obey whatever the cosine value you have from calculator. Stick it in there. Positive as it is positive. Negative as it is negative there. And then this will always work. This is known as law of cosine. This is how you're going to remember the law of cosine. Not as it is A, B, C. Oh, they call this one C, so this is going to be C. Not like that. It's relative location. When you applied law of cosine, there was only one angle of interest here. You look at this angle right there. What's the right-hand side? Right-hand side is all about two adjacent sides. If you see the right-hand side, what's involved is all about the two adjacent side, right? What's the left-hand side? Is opposite side. So if they name differently, and if you turn it around and all things like that, that's what you have to focus. Here's my angle theta. I'm going to apply law of cosine to that angle. Then right-hand side is about two adjacent side. The left-hand side is the opposite side, right? These A, B, C are relative terms for angle, not absolute letter system. All right, let's look at example. And my usual suggestion is that